some beautiful things that surprised me starting out as a theoretical astrophysicist, but sort of getting closer to things that I thought were just entirely theoretical becoming quite real and more beautiful than you could have ever imagined. So I'll give you some of these things that will feature said duck. But first of all, I just want to say something about Rosemary's teaching legacy. It's been my great privilege to teach with Rosemary over many years. I thought it was typified by, this is one of our honours students, Joanna Shepherd, who left in 2020. And I asked her at our alumni night, what was the thing that was really useful to you out of Monash? What do you think was the most useful thing in your undergraduate? She said, the most useful thing I learned at Monash was orbital dynamics. And that, I mean, it's very directly relevant to a job, which is controlling satellites go around the Earth. But this kind of comments come out quite frequently, and so like teaching reviews, Rosemary's style of teaching is very effective. Dynamics is like the most interesting part of learning astrophysics. Great to get into mathsier stuff, which Rosemary was certainly always very strong on, was keeping it rigorous and not washing it down into like kiddie talk about things, but giving you the real meat. This kind of burns a little bit because mine is the other 1/3 of the unit, but. But absolutely, it's that's one of the fun things at Monash has been that dynamics has always been like a real foundation in our astrophysics teaching, and that's gone all the way through. But so let's go a little trip on memory lane. For me, it's back to 1995 when this story starts. So, anyone remember things about 1995? Well, if you remember Windows 95. So I finished high school in 1995, which is a significant year because. Also, Carlton won the AFL Premiership, which now feels like a very long time ago, including after last week. The O.J. Simpson trial happened in 1995. Anyone remembers that? It was, according to Wikipedia, it's the beginning of the information age because it's when the internet was first privatized and then became a thing that was not government run. But more importantly to this story, it was the discovery of the first planet going around a sun-like star. And as that's been a big part, as you already heard, of Rosemary's career, because that subject just exploded. Excuse the commas, but that's 1995, the year. And here we are in 2024, and so that's gone from one planet known around another star to 5,500, and this is just an exponential increase in discovery that's completely changed. And of course, most of that was completely unexpected, including the discovery in 1995, which is that no one had any idea that there were planets very much unlike the solar system, where you got a Jupiter in a 4-day orbit around a sun-like star. Nobody was expecting that. And that's why things like tides and resonance became like a hot topic, because we found these tightly packed planetary systems where everything's like tucked in tight, that are nothing like what we find in the solar system. So my questions, sort of come a bit later in that story, which is we started in 2015 to start to get images. Now that's typically what you'd find from a telescope pre-2015 of the places where these planets are actually made. What changed in 2015 is we had this telescope come online called the ALMA telescope, which is a series of dishes that are hooked up together as an interferometer. Some magic Fourier transform happens, and you can get an image of the same thing, same wavelengths. So this is at sub-millimeter wavelengths. Actually, it's about 1 millimeter, this image. And you get a resolved image of the disk of gas and dust around a distant star. So planet formation, very much like extrasolar planets, was a story that was focused on the solar system and how our solar system was born. And there's a lot of unanswered questions there, because it's a really hard problem. But what we have is now fresh data where we can see some kind of disk of gas and dust around another star, and what we'd like to know is what's going on inside, because that's what we'd like to know about how planets are made. So we were quite well prepared for this story at the time, because I'd just been working with a postdoc actually in the maths department, Guillaume Leb, and we'd been doing some mathematical development of being able to simulate gas and dust mixtures. So a protoplanetary disk like this is a very good just mixture of gas and dust. And what do we call dust? Just anything that doesn't feel gas pressure. So if I drop a rock in the room, it drops to the floor. And so you can think of the same thing happening if rocks get big enough. So things like, the best analogy is something like smoke. So smoke will stick to the gas. whereas like bigger rock will just fall to the ground. That's the same thing that happens in a disk like this. So we were able to model this, and this sort of game had been done for a while where people stick planets in disks and watch the little wake that happens as the planets orbit. But if you do that in a sort of gas-dust mixture, you see the dust forms this very thin layer. And actually that sort of thin layer is what you're observing at these millimeter wavelengths. In fact, if we see them edge on, we can see that they're quite razor thin. And so therefore, when people were starting to talk about what makes these gaps and rings, there was a lot of controversy because the gaps and rings in your image look very axisymmetric, but people thought the planets should make spirals. And so there's no spirals here, so it can't be planets because it's just like axisymmetric rings. And of course, we said, well, the answer is you're not observing the gas disk where the spirals are. You're observing this quite thin pancake where you've got embedded bodies, but in a very thin disk. All right, so we can make actually a direct image that compares with that original ALMA image and say, well, look, now the conclusion here is terrifying because the kind of planets you need to put in to make these kind of gaps are like Jupiter mass planets. But this thing is like one of a very young object. So it's an object which is like in the process, still got smush arriving at it from forming the star. So that's what we'd call the very early phases of star formation. There's a lot of mess going on from the environment. But if we've got fully formed Jupiter mass planets, that implies that planet formation is done. As in the context of the solar system, you're supposed to build rocky things first, and then the rocky things become bigger things, and bigger things become bigger things. 10 million years later, you're supposed to have gas giants. This thing's less than 1 million years old, and if that conclusion's true, so a lot of then it's terrifying for that planet formation seems to happen much faster than we imagined. And so a lot of our work since has been to try and figure out, is this really true? This is just modeling, like who cares, you're just a theorist. But is it really true that there's really planets, newborn planets responsible for these things? And of course, a bit like the exoplanet story, the observations exploded with lots more of these observations of same kind of thing around other young stars. So definition of a young star is just that it has a disk of gas and dust around it. So, but this is the same thing. These are imaged at millimeter wavelengths. They're hundreds of AU in size. So actually, most of these are much bigger than the solar system. And that's probably just a selection effect. They're the big bright ones that we like to go and observe. But you can see the same story is true. Gaps and rings everywhere, holes in the middle. But can we relate this back to planets? Because if we can, then it has big implications. There's a really good analogy actually in the solar system. Our nearest proto-moon disk is actually just the rings around Saturn, and you can actually see the same physics going on in the sense that we have embedded bodies that are carving gaps. This is Daphnis carving the Keeler gap in Saturn's rings. Now, there's I'm going to give sorry Rosemary, I should have done equations here. I'm going to give the no equations version like we would do in first year ASP. If we've got a star and a planet, there's some basic interactions going on that give you this like nice looking spiral wake from the planet. And the physics is actually really beautiful and actually very well understood analytically, which is the planet excites a disturbance at the resonant frequencies of its orbit, and that these add constructively to give you this kind of inward propagating wave and an outward propagating wave. So the basic analogy is very much like a duck. So like a planet is just like a duck swimming in its lake, and the duck excites waves in the surface of the lake. So these waves constructively interfere to give you a kind of this classic Kelvin wake, which is the line of interference of all the waves excited by the duck. Now a planet is just the same, but the lake is a bit different. What's different with the lake? So the duck swims and the water goes behind. The only difference with the planet is the inside of the planet, the fluid goes ahead. So instead of that, so that's one of the wakes going that way, but the other wake goes that way. So that's really the only difference, is because the differential rotation, the stuff on the inside is moving faster than the duck. And hence, that's the basic explanation for why these planet wakes exist. In fact, you can derive a lovely analytical formula for the shape of this wake in its environment. And one of the big breakthroughs for us was actually detecting the signature of this kind of wake as a velocity perturbation. So the planet disturbs a little velocity. And I'm trying to skip things, so I've got a few slides here. But basically, you can map the Doppler shifts in a spectral line. You can make a model. You can predict what the wake from a planet would look like. And you can see that you get this little wiggle in what's called a channel map, which is a slice in frequency of the emission line. So it's like a weird sort of cut through a protostellar disk. of all the material that's coming towards you at a particular velocity. And if it was a nice axisymmetric disk, you would have a reflective symmetry where this thing on the other side will be the same thing as this on that side, but it's not, and we think that's directly due to detecting this wake from an embedded planet. Okay, so again, that's a little indirect though, in the sense of it's a velocity perturbation that's a little indirect, but we've also been fortunate in a couple of cases at least to now have like actual just direct images. So this is some work with Ian, who's sitting right in there in the third row, where we just gone back in the archives and imaged a newborn planet in one of these gaps in a disk, and it's just tracked it through the archives over 4 years or so. You should be able to see there's a little bit of motion there. This is the most famous one called PDS 70, where you can see there's a planet there, there's another one that's there, and well, let's talk about that one in a second. But we can now directly see, okay, we've definitely got something. I don't know exactly what it is, but it's a moving blob that's probably, multi-Jupiter mass planet that's orbiting in this kind of gap in this disk. So it's pretty direct evidence that the story we started with is probably true. All right, so just a little teaser there, not for the recording. This is from Ian and about to be submitted on Monday, isn't it? Which is that Ian's gone back looking in the archives, and there seems to be a third thing here. And this goes back to the story about resonance, is you've got these sort of seemingly tightly packed planets. When Ian's done the orbital fitting for this, it seems to be true that what we have is like 3 planets, and the orbits that we fit seem to be consistent with being like in a 1, 2, 4, which is called a Laplace resonance. And the most famous example of that is the Galilean moons. They're famously in a sort of tightly packed configuration like that. So again, that would be the same. It's the same physics. It's gravity. It's planets being pushed to migrate in a disk, and we seem to be seeing that in nature. So having studied this sort of stuff theoretically, seeing it for real is pretty special. The other one that we studied a lot theoretically is related to this sort of 3-body problem. Is if you have some sort of material orbiting around a binary star, then obviously there's some point where those orbits go unstable, and you end up having like a big hole in the middle of your disk. So again, this is way back in the 90s, 1994. There's a little one on the plot here, so this is like the size of this cavity as a function of eccentricity. Little object on that plot called GW Ori, and so that same thing is true. So if you start to look at these observations of these sort of disks around young stars, there's an awful lot of them with big holes in the middle. And these are all misnamed. They're all called transition disks because people think they're like some kind of photoevaporation from the central star. It's all rubbish, basically. Because you can see if you start to look in other wavelengths, so these are in millimeter wavelengths, this is in optical wavelengths. This is what you call scattered light image, which is starlight reflected off the surroundings. You can see all these like wonderful spiral arms. And there's only way you can get wonderful spiral arms, and that's by like having other companions or heavy bodies involved in the shaping of these things. So one of the funky ways that a binary can shape a disk is not only carving a hole in the middle, but if you misalign the binary, then you cause what's called nodal precession. So the orbits tend to precess, and the inner parts of the disk want to come into the plane of the binary. But precession is a very differential thing. We did this in the lab in second year this week, which is the precession goes like 1r cubed. So it's very good at aligning the inner regions and very poor at aligning the outer regions into the binary plane. And so my colleague, we kind of did this theoretically like way back, thinking like this is fun. It's like makes a cool movie and looks like a sort of fun phenomena where you get this kind of what we call disk tearing, which is a binary can kind of rip off this disk into independent rings that then precess at different rates and all go around each other, and lots of fun stuff happens. And at the time, actually, we were interested in black holes. I'm interested in spinning black holes doing this, but it turns out binaries do the same thing. And this is fun because never in my life would I thought we might observe anything like this, but here it is. So this is GW Ori, actually the same one that was back on the original slide, and you get this series of independent precessing rings. It's actually a triple. But it's driving this precession. You can see these independent like rings appearing on the sky. Like it's really wonderful. And as a theorist, I just never dreamed that we'd like actually observe this stuff and go, have your ideas actually tested by nature in a very short time scale. So the other thing that's been quite beautiful is this kind of, as Rosemary talked about, putting planet formation in this early stage actually means there's a lot of violent things going on. Now we've got direct evidence for that sort of stuff. There's a lot of disks, for example, where you can see there's been a violent interaction. where there's material sprayed between the objects and some kind of interaction's gone on. And that can also help us solve old mysteries. So here's one called Ori, which is like a really old problem, because in 1936 it went bang, and sorry, this is astronomers' units, so this is faint and this is bright, even though this is 16 and this is 10, we're in magnitudes. So it went very bright by about 2 orders of magnitude in less than a year, and it just stayed bright for like 100 years ever since. And the mystery there is always what made that go bang. But now we've got images, we can start to just think about what sort of scenario that might actually be. And we found, for example, in some recent work, that if you just smack 2 things together like this in a kind of stellar interaction, that you can get this very rapid accretion rate rise. Actually tends to be on the low mass object, and that is would exactly correspond to like a bright burst. And I'm out of town, so I'll finish there. But basically the story is dynamics is beautiful. That this tidal truncation actually seems to be the main thing shaping these planet-forming disks, is all interaction with bodies and companions and all that kind of thing. But warping and breaking was also kind of something we had sort of worked on, but we didn't really expect to see in nature. It seems to be actually very common. And the planets seem to form like disturbingly quickly, and this story seems to have held out over the last 10 years at least. So there's plenty more to do, but thanks Rosemary for the inspiration. I don't know if I can share myself.